Have you ever gazed at the night sky and wondered if we are truly alone in this vast universe? Each twinkling star, a burning beacon in the cosmos, might be hosting planets with conditions ripe for life. We are inhabitants of a tiny blue dot, suspended in a sunbeam amidst a galaxy of 100 billion stars, which is just one among 2 trillion galaxies in the observable universe. That's a lot of zeros, a lot of possibilities, an unimaginable expanse of cosmic real estate. When we ponder these enormous numbers, it feels almost absurd to consider that Earth is the only planet to harbor life. The universe is vast, ancient, and filled with an unimaginable number of celestial bodies. With such unfathomable breadth and depth, it seems likely that somewhere out there, perhaps on a distant exoplanet orbiting a far-off star, life might have taken root. Maybe it's just simple bacterial life, or perhaps it's an advanced civilization, gazing back at us, pondering the same existential questions. But how can we even begin to estimate the probability of life existing elsewhere? Here is where a mathematical tool known as Drake's equation comes into play. Formulated in 1961 by astrophysicist Frank Drake, not to find a definitive answer, but to stimulate scientific dialogue at the first scientific meeting on the search for extraterrestrial intelligence. This equation is a probabilistic argument used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It considers factors such as the rate of star formation, the fraction of those stars with planetary systems, the number of planets that could potentially support life, the fraction of planets where life actually develops, the proportion of life that develops into intelligent beings, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and the length of time such civilizations release detectable signals. If this piques your curiosity, prepare to delve into the fascinating world of Drake's equation. In the vastness of the cosmos, we are on a quest to uncover our cosmic companions if they exist. Let's journey together as we unlock the mysteries of our universe. Drake's equation begins with the rate of star formation in our galaxy. This is the first factor of the equation, and it sets the stage for the cosmic lottery that is the search for extraterrestrial life. Now, when we talk about the rate of star formation, we're referring to how many new stars are born in our galaxy every year. In the grand theater of the cosmos, stars are the stages upon which the drama of life may potentially unfold. You see, stars are not just twinkling lights in the night sky. They are the forges of life's essential elements, and the crucibles around which planets form. The rate of star formation is significant because each new star increases the odds of a life-supporting planet. The greater the number of stars, the greater the number of planets, and thus, the greater the chances for life as we know it to exist somewhere out there. Scientists estimate that there are approximately 400 billion stars in the Milky Way alone. And with an estimated 1 to 3 new stars forming every year in our galaxy, the numbers start to add up pretty quickly. But it's not just about the numbers. It's about the potential each star holds. Each star could host a planetary system, and each planet in that system could potentially have the right conditions for life to emerge. And that's where the rest of Drake's equation comes into play. However, it's important to remember that while the rate of star formation is a key factor in Drake's equation, it is only the beginning. The equation incorporates several other factors, each of which further refines our understanding of the likelihood of extraterrestrial life. With billions of stars forming every year, the potential for life-giving planets is astronomical. As we delve deeper into Drake's equation, the cosmic odds may seem daunting, but they also remind us of the immense possibilities that lie in the vast expanse of the universe. The equation continues with the fraction of those stars that have planetary systems. This factor, represented by the variable FPE, is crucial in Drake's equation. It's the percentage of stars that are orbited by planets. To understand the magnitude of this factor, let's take a step back. There are about 200 billion stars in the Milky Way galaxy alone. If only a small fraction of these stars have planets, we're still talking about a mind-boggling number of potential worlds. But how do we determine this fraction? Enter exoplanets. These are planets located outside of our solar system, orbiting stars other than our sun. For a long time, exoplanets were the stuff of science fiction, but that all changed in the mid-90s. Scientists, using cutting-edge technology and highly innovative methods, began to confirm the existence of these distant worlds. The discovery of exoplanets has revolutionized our understanding of the universe and has had a significant impact on Drake's equation. Every new exoplanet discovery potentially increases the value of FP, bringing us closer to an answer. As of now, we know of over 4,000 confirmed exoplanets. These discoveries have shown us that planetary systems are not a rarity, but rather a common occurrence in our galaxy. They've also revealed a stunning diversity of planets, from gas giants larger than Jupiter to rocky worlds similar to Earth. These discoveries have further implications. They suggest that there are likely countless more exoplanets waiting to be found, orbiting stars too distant or faint for our current technology to detect. As our technology improves, the number of known exoplanets will only continue to grow. In essence, the second factor in Drake's equation is a testament to our ever-expanding knowledge of the universe. It's a factor that's subject to change as we learn more, and it's one that holds a great deal of promise for those searching for signs of life beyond Earth. The discovery of exoplanets brings us closer to finding potential homes for extraterrestrial life. Next in the equation is the number of planets that could potentially support life. Now, this is where the Drake equation starts to get really fascinating. It's not just about the number of stars or planets out there, but about the ones with the right conditions for life to thrive. So, what exactly are these conditions? The first thing that comes to mind is water. All life as we know it needs water to survive. But it's not just about having water, it's about having liquid water. That means the planet needs to be at just the right distance from its star, the so-called Goldilocks zone, where it's not too hot, not too cold, but just right. Then there's the question of a breathable atmosphere. For life as we understand it, that means an atmosphere with a mix of gases, including oxygen. But who's to say that other forms of life couldn't exist in different atmospheric conditions? We also have to consider the planet's size and its gravitational pull. Too big, and the gravity could be crushing. Too small, and the planet might not be able to hold onto an atmosphere at all. And there's the matter of time. Life takes time to develop and evolve. So a planet needs to be not just in the right place, but at the right point in its life cycle. When you consider all these factors, you might start to think that finding another Earth seems like finding a needle in a cosmic haystack. But remember, there are billions upon billions of stars in our galaxy alone, each potentially with its own solar system of planets. So, how common are these life-friendly conditions in the universe? That's still a matter of debate among scientists. Some think they're quite common, while others believe they're incredibly rare. But one thing's for sure, the more we learn about the universe, the more places we find where life might exist. The equation concludes with the lifespan of a communicating civilization. The final elements of Drake's equation are nothing short of fascinating. We consider the fraction of life-supporting planets that actually develop life. This factor alone raises profound questions. How often does life triumph over the inhospitable conditions that might exist on another planet? Next, we ponder the fraction of life that evolves into intelligent beings. The leap from single-celled organisms to creatures capable of understanding their place in the universe is a monumental one. How common is this leap? We then consider the fraction of intelligent life that develops technology, specifically technology that enables communication across the cosmos. It's a reminder that intelligence and technological advancement are not always synonymous. Finally, we consider the lifespan of a communicating civilization. How long can a civilization sustain the use of technology without self-destruction or succumbing to external threats? These final factors remind us that even if life is common, intelligent, communicating life may be rare. So, what does Drake's equation really tell us about the existence of extraterrestrial life? In essence, Drake's equation is a probabilistic argument. It uses the multiplication of several factors to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Each factor represents an element of uncertainty, from the rate of star formation, to the proportion of those stars with planetary systems, to the number of planets that might develop life. The beauty of this equation lies in its simplicity and its power to spark our imagination. It doesn't provide a concrete number, but it does offer a framework for scientists to explore the vast possibilities of life beyond Earth. However, each factor is laden with uncertainty, and our understanding is continually evolving, so the equation's outcome varies wildly depending on the values we input. Drake's equation may not give us a definitive answer, but it certainly provides food for thought on our place in the universe.